Hey, I'm going to try to make this video a bit shorter. Last one was kind of long. You know, I just yapped. I yapped too much. I would not stop talking and reiterating myself. So I'm going to make this one faster. We have a lot of content to cover today. So, kind of done talking about stuff we can do with first derivatives. We're almost done with derivatives generally. We're about to kind of move on to other things. We'll come back to derivatives more later. But to kind of wrap up this derivatives unit, we're going to talk more about second derivatives, what we can do with second derivatives, and kind of brush up more on concavity, right? Things we can assume, things we can do. Now, a very long time ago, we talked about critical numbers and finding extrema using the first derivative test. Remember, we had that number line, and we'd have our critical numbers. We'd plug in values on both sides to figure out if our function was kind of increasing or decreasing, and then we could use that to find the coordinates or locations of a extrema, whether that be a maximum or a minimum, right? We also talked about concavity a while ago. Concave up, right, kind of looks like a cup. Concave down looks like a frown, right? We'll go back to that more in this video. Concavity and second derivatives are related, thoroughly actually. The sign of your second derivative determines concavity. So now, going back to what I said about the first derivative test, there's also a second derivative test. Now, trust me, there are not more. There's no third derivative test, at least not one that I know of. Definitely not one that we're using in this kind of level of calculus. Now, the second derivative test is going to allow us to kind of combine a critical number with the concavity state of your function at that critical number. So what I mean by this is you have a critical number. You have a critical number somewhere. Let's say that's at x equals c. Right. Now, at x equals c, if you have a concave down function, you're going to see something versus if you have a concave up function. And I mean specifically at the critical number. When we did our first derivative test, right, we were looking on values. We were looking for values on either side of our derivative or our critical number. But for the second derivative test, we are looking at the critical number, not on both sides, not on one side or anything, at the critical number. That's very, very important, right? Now, if you have a concave down function at a critical number, meaning your function is concave down instantaneously at the critical number, you're going to see a relative maximum, right? Now, if you have a concave up function at the instant moment you have a critical number, you're going to have a relative minimum, right? Now we can, looking at this on a graph, right, if we have kind of y equals x squared right here at x equals 0, we know this function is concave up the whole time, and we have a critical number, we know that there's a relative minimum, right? And these are kind of definitions, things we've noticed over many years of calculus, that the concavity state of a function actually does allow us to determine the identity of an extrema, whether that be a maximum or minimum, given a second derivative, right? We don't necessarily need to know what an actual function is, and we're going to do that as an example here. Because sometimes you'll be given a weird formula, such as, let's say, I'll be up here, dy dx is equal to y plus x. So kind of like an implicit function. We're given a derivative here. Now, I can tell you right now, just given this derivative, I can find where there may be relative maximums and relative minimums on the function, right, y or f of x, given its derivative. So using the second derivative test, we can find extrema on this function, right? Very interesting. So now kind of in a problem you'd be asked, now given this function, or given its derivative, determine if the point, and then they'll give you a point, and they'll say what type of extrema that point is. Or maybe just find an extrema. In this case, I'm going to just plug in the point 0, 0, because if I plug in 0, 0 here, we know dy dx is going to be equal to 0. Now, you can plug in 2, negative 2, negative 2, 2. Really, this is kind of like a mirrored function there. Now, I'm going to erase this, and we're going to go through my process of the second derivative test, right? let's look at the point 0, 0, because we know that plugging in 0, 0 to dy dx will output a critical number, a value in which our derivative is equal to 0 or does not exist. I'm not going to be worrying about does not exist derivatives, because as we've seen in the past, generally when you have critical numbers at points where your derivative does not exist, weird things happen. A lot of times you don't have an extrema, right? So let's begin. We know dy dx, given that when we're plugging in this whole point, we can plug in an entire point to a derivative. It's going to equal 0 plus 0 is equal to 0. Right, so we have a critical number at 0, 0. So critical number 0, 0, or at x equals 0, or at y equals 0, whatever you're looking at. Now, is 0, 0 a relative maximum, a relative minimum, or neither? Let me show you how to find that. We can find the second derivative, right? D squared y over dx squared. The second derivative, we're going to use implicit differentiation here. Remember, we know how to do that. We're going to take the derivative of this function dy dx. Well, okay, the derivative of y is dy dx, and the derivative of x is just 1, right? We're deriving with respect to x, so the x terms can just be derived normally. This technically would be chain rule times dx dx. We don't really need to worry about that because dx dx is just equal to 1, right? So now, what do we do with this? Well, and something I'll warn you about, especially if you go further in math, always want to tell yourself, substitution, substitution. Can I look at a function? Can I replace a variable with something I already know, right? And also a chain rule. When you look at a calculus problem, chain rule, substitution, substitution, chain rule, substitution, right? That's what I always do, right? Dy dx, well, dy dx is right here. Dy dx is equal to x plus y. So d squared y plus over dx squared is equal to x plus y plus 1. It's that easy, right? I think honestly the hardest part is recognizing that you can do something with this dy dx, because it's really easy to think, okay, what do I plug in? There's no variables I can plug in. I don't have a value for a derivative or anything. Well, you can substitute in that derivative, right? Or you also could just notice that we're dealing with 0, 0 here. We're going to end up plugging in 0, 0, and it's not going to matter. Those are going to cancel out. But substitutions are going to come in handy when we're dealing with, especially implicit differentiation, especially with second derivative test. Right, now, so we have our second derivative. Going over here, we're going to find what our second derivative is equal to at 0, 0. It's equal to 1. Right, okay, so the second derivative is equal to 1 at 0, 0. That's a positive value. 1 is greater than 0, right? That's a 1. Sorry, it kind of looks like a 2 there. Now, if you remember conditions for concavity, if your second derivative is positive, you're concave up, right? Now, if your second derivative is negative, you're concave down. Because what concave up means is your slope is increasing. Your function is going to be increasing at an increasing rate, right? So our second derivative is 1, which is a positive value, which means our derivative is going to be increasing, which means our function is going to be concave up, right? So because our function is concave up at 0, 0, which is a critical number, we're going to have a relative minimum. Remember, you can kind of always draw this out yourself. Concave up looks like a cup, you're going to have a relative minimum. Concave down looks like a frown, you're going to have a relative maximum. So we've determined that at 0, 0, we have our function is concave up instantaneously, and as such, we have a relative minimum. Right. And that's really all for the second derivative test. It's not super difficult. I will say one thing. If you try this and you get a value of 0, or your second derivative doesn't exist, right, you're going to have to resort to the first derivative test, the one with the number line, plugging in values on both sides. But generally, especially if you're in a class doing this for a problem, you're not going to be given a first derivative and be asked to use the first derivative test, right? Because you need Because generally they'll be testing for the second derivative test, right? See if you know that. However, on the number line, well, no, sorry. It's simply not possible because you would need to find f of x values, right? Yeah. Yes. Yeah. Okay. Anyways, I'm yapping. We're gonna talk about this kind of concept called I've heard of it like zooming in, linearization, local assumptions of a function. Right, that's not in the title. It'll be in the title of this video, but it's not right on the board now. Essentially, kind of another thing we can do with second derivatives stems from this kind of idea of infinitely small things, right? Let's say we have a function that's going to look like this, right? Similar to the one used in the MVT video. Actually, I'm going to make this function kind of more curved, right? Now, if we were to really zoom in, if we were to really zoom in here, right, and graph just this part, but super zoomed in, it would kind of look like this, and we can zoom in further. And what we see is that if we keep zooming in and zooming in and zooming in, eventually our function really very closely resembles a straight line. And so we can kind of think of every function as just infinitely many straight lines kind of combined together, right? On the very, very smallest level, infinitesimals and all that, right? And so knowing this, what we can do is with calculus, we can make near perfect approximations with tangent lines, right? And we've discussed this as a concept before. The closer you are to the origin at which your tangent line is focused on, the more accurate your approximation will be, right? Now, how does this tie to concavity, right? We can make an estimate that's really, really close to perfect. However, there's always going to be some error if we're using a tangent line to approximate a function, even if we're super far zoomed in and our function is essentially linear, right? Now, we can kind of make assumptions about what this error looks like using concavity, right? So I'm going to draw out this function y equals x squared. It's a parabolic function, right? If I were to draw a tangent line, what's going to happen is any value on this function that I try to approximate, I will underestimate the actual value. Now, what I mean by that, if I try to approximate a value out here, well, it's going to be pretty inaccurate, but I'm going to use this value on the tangent line, right? Because I'm gonna come up with a slope for that tangent line. I'm going to find a point for where that tangent line is focused on right here, and then I can come up with an equation for a line, right? A whole line, y minus y1 equals m times x minus x1, right? And then I can use that line to approximate a function value over here. It's going to be pretty inaccurate and there's going to be some error, but I choose this because it really shows that if we use this line, the value we're going to get from our tangent line is going to be far lower than the actual value of the function. And as we get closer, that error is going to decrease. However, there's still always going to be that error. Now, concavity. I said this is a parabolic function. Let's say this is just y equals x squared. Now, if you take the first derivative of this, you get 2x. Take the second derivative, you get 2. Now, 2 is greater than 0. X squared, as a function, is always concave up. Always concave up. Now, what we see is that tangent lines will underestimate functions that are concave up, or rather, underestimate intervals that are concave up. Now, if I were to draw negative x squared, that function, its first derivative is negative 2x, second derivative negative 2, which is less than 0. So negative x squared is always concave down. And the opposite is true. If I draw a tangent line, I'm always going to overestimate the function. So we overestimate concave down functions, right? Or concave down intervals. Now, this is, with local linearization, zooming in really, really far, sometimes they'll call local linearization textbooks or classes, right? There, the error gets really, really, really small as you zoom in. However, you can, even if you can't see necessarily a function because changes are really, really small, you can use concavity to tell if you're overestimating a function or underestimating a function. Sometimes that's useful information. Sometimes you're doing an experiment and you don't necessarily have the tools or knowledge to approximate an exact value of something, but you can use an approximation. So being able to tell, somebody, a company or a professor or teacher, somebody, if you're overestimating or underestimating values consistently will help kind of allow your results to be interpreted and applied better, right? And that's kind of like a more of a real sense, right? And let's say you're like an engineer, you're making a product, you want that product to be as close to exact as possible, but you still have to use an approximation, right? You can use concavity knowledge to know, okay, maybe my product isn't that actually perfect. It's overestimating a little bit because my kind of variable of interest is concave down on this interval, right? Anyways, I'm yapping, right? That's really all I have today for second derivatives and concavity, how we can over or underestimate functions, how we can tell if we're over or underestimating functions given concavity information, and lastly, how we can use a second derivative test. That's an important one. It's a useful one, kind of how like L'Hopital's rule is a kind of a good shortcut for limits. Second derivative test, generally going to be faster and easier than that first derivative test. Use it when possible, right? Anyways, that's all I have for today. Bit of a shorter video. See ya, class.